if a person is colorblind, there's kind of this misconception that they just see in black and white or in shades of gray. I don't know how common this is, but I want to say that's a type of color blindness, but it's by far not the most common. There's red-green color blindness, which means that if you have a red dot and a green dot, that it's difficult to tell the difference between them because, we'll say from black to white, that scale, they're sort of in the same place. They might be different on the color spectrum, but in how bright they are compared to black and compared to white, they're pretty much equal, and so it's hard to see. And it's my understanding that both of these would look kind of blue. I'm not colorblind, so I can't tell you for sure, but the red-green color blindness, from what I understand, it's these colors generally just come out blue. That doesn't mean everything's blue. I think they can still see orange and yellow and such. This would be different. So you've seen the color blindness tests where they kind of have a bunch of dots arranged in a circle, and they would all be the same size, and then they would draw out maybe a number 4 in one style of dot, and then the rest of them would be other colors. And then in theory, since all the dots are the same shape and they look sort of randomly aligned, then someone who's colorblind would just see a whole bunch of dots the same color and they would say, I don't know what that is. But then someone who can see colors well would say that's a 4. So that's sort of the test for it, is they have those things. And the real reason why colorblindness happens is, I said in the eyeball video that in the back of the eye, that's the pupil up there, the back of the eye is covered in little rods and cones. Okay? And I'm only drawing a few of them, but really it would be, covered in them, completely coated. And the rods pick up low light, but they don't see in color. And then the cones, I said, are the ones responsible for color, and they only work when it's kind of bright in the room or bright outside. And the cones come in 3 different varieties, and they're commonly called, even though this is incorrect, red, let's spell things right, red, I'm having a terrible time, green, and blue, but really they're more like red, green, and yellow, or greenish yellow. And I'm gonna draw out the color spectrum for you. I'll use gray for the background color. Okay, so this is sort of getting into physics, but it's important to understanding why this actually happens the way it does in the eye. So this is just the visible section. It goes for really low microwaves all the way to really high gamma waves and stuff. But this is just the visible part, and colors actually go in a line. I want to make that clear. So down here is violet toward the lower end of the number line. I don't know the actual numbers. And towards the higher end is red, and that's why we have infrared and ultraviolet. Infra means higher. So you know how this is the rainbow. This is the color spectrum. We have orange and yellow, green, blue, and I think indigo is what's right here. I don't know if I have an indigo. I'll try. indigo. It looks like these two should maybe be switched, but generally I have this pretty close to right. And so this is where our rainbow comes from. You can imagine this, you know, the violet would move a little bit, the red would arc all the way across the sky. And this is a more physically accurate way of showing what colors are. We have that color wheel that's all divided up, and it makes it seem like red is next to purple when you do it that way. But the color wheel is a byproduct of how these rods work, and I'll show that here. I said there's three different types of or how the cones work. There's three different types of cones, and one of them, I don't know what color to use. Well, I'll just use the right colors, I guess. One of them has its peak sensitivity around red. Okay. One of them has its peak sensitivity around green. And the other one's yellow. Well, now I'm not sure how we get purple. I think maybe the green is just bigger. Yeah, I think they're just supposed to be really big. Because, I guess to sort of explain why it's so shifted toward this side, you know, the sun gives off mostly orange and red, yellow light, and that's why plants suck up all of these, and they leave behind mostly green light. So we'll just say that this green one comes all the way to violet. Again, I'm not completely sure that I'm getting it rigorously correct, but this is just the intuition of how this works. So green catches everything in here, and yellow catches everything in here, and the red cones see all the light in here, but they have peak sensitivities. One of them is mostly attuned to green wavelengths of light, and red is mostly up here. So if a photon comes in that is, just to not use the correct colors, I think I'll go this one. If a photon comes in at exactly this wavelength, then both of these, the yellow, well, we call yellow-blue, two of them get activated and the red one doesn't, and so your brain figures out, oh, I'm getting a lot of stimulation on this one and a lot of stimulation on this one, so I know that the color belongs right here on the color spectrum, and I'm going to interpret that as a yellowish green. If we get a photon that's down here, if one of these lower wavelengths, or longer, and then up here they're higher and higher, I don't know, that would be in physics if you want more of an explanation of these wavelengths things. But if what we would call indigo light hits our eye, then only these green rods, no, cones, only these green cones are activated, and the yellow and red ones aren't. And then your brain says, well, it's stimulated not all that much, so I know it's indigo. If it would have been stimulated this much, then I would say it's blue. And every single cone, you know, does this, or well, I guess every set of three, or in every position on the back of your eye. So rather than getting absolute colors, like, it's sort of just made of these primary colors in a way. Like, if you look at one of the big boxy TVs, I'll try to draw one. If you look at one of those, you'll see it's just made of like three different colors, and it's just dots everywhere. But then if you look at one of the flat panels, the widescreens, then it has like absolute colors, and no matter how close you get to the screen, you can still see independent slight variations in color. So your brain actually works more like this, and a lot of our vision isn't very good. Like I discussed before how the nerves come into the eye and then out through the optic nerve, or into the optic nerve, and then all these nerves on the inside of your eye eye reflect the light a little bit, and so that gives you a fuzzier picture. And also you have 3 different things sensing color rather than just one for every position, and you have rods and cones, and so there's another just almost unnecessary complication, even though these complement each other well. A lot of what we consider seeing actually happens in the brain. The eye is almost a really bad instrument for doing this. Modern cameras are much better at capturing images than our eyes are. And if our brains weren't specifically made for interpreting this bad information, we wouldn't be able to see it all. So I guess I started with colorblindness. I hope you have a little bit more compassion for your colorblind friends now after seeing this video, and now you can be a little more sensitive to their most likely red-green colorblind, but there are other types. I forget what they are, but it's usually just 1 or 2 colors that they have trouble telling the difference between, so you don't have to think anymore that they can only see in black and white.